Will we need MATLAB for this lecture, Professor?
Not today.
Not today?
Wednesday we'll be using MATLAB.
Okay, cool. And then as far as the homework, will you be posting the solutions or will you be going over the homework?
Yeah, so I'll be after you guys submit it, I'll be grading them, and then a few days later I'll post the solutions for the homework.
Okay, cool. Thank you.
Yeah. But if you want me to go over anything in the lecture, you can just ask me too anytime.
Okay, cool. Yeah, I had I think 3C.
Okay. Yeah.
I kind of got close to it, but I had a lot of other homework that I had to tackle. So like I was like, I tried to join your office hours today, but I got caught up at work.
Okay. Yeah, we can. I can go over that one real quick in the beginning of class today.
Thank you. Appreciate it.
Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everyone doing today?
Good.
Good. Anyone else watch the Super Bowl yesterday?
Oh no.
It's okay. It wasn't the most exciting game.
Yeah.
After the first half, I kind of did something else, and I feel like I didn't really miss anything. But congrats to Tom Brady. He's one of the greatest. Yeah. I used to hate him because he used to be on the Patriots, but strangely now that he's not on the Patriots, I was like kind of happy for him after yesterday.
Yeah.
Okay. All right. So the plan for today is I have just a tiny little bit of the lecture notes I wanted to finish up from last week. So that's talking about the errors that can occur. So I have one more error I want to talk about, and then from there we're going to start the next set of lecture notes, which is how to actually solve diffusion equations with finite difference. Okay. And so if you weren't here at the very beginning of lecture today, the plan is for today I'm going to go over kind of the theory behind it. How do we apply finite difference to a diffusion equation, and then Wednesday we'll talk about how do we actually implement it in MATLAB. Okay. But before all of that, I know there's some questions on problem 3C on the homework. So I'm going to go over that kind of first thing right after this. Okay. Okay. So besides problem 3C on the homework, are there any questions that I can answer? Okay. All right. So let's go over problem 3C on the homework. Okay. So across this class and across one of my other classes where I kind of assigned the same problem, there's been a lot of questions on this one because it's a tricky one, right? All right, so in 3C, we basically have a matrix that we want to fill out with a for loop, right? And so our matrix looks like this. All right, so we have a first row, which is -2, 1, 0, 0, 0. And then we have 1, minus 2, 1, 0, 0. And 0, 1, minus 2, 1, 0, 0, 0, 1, minus 2, 1. Right? And then 0, 0, 0, 1, minus 2. Okay. And so there's a pattern here. So you can see we have minus 2 on the diagonal, and you know, a 1 on the off diagonals. Yep. I'm not giving you the solution. I'm just giving you help on this. Yeah. So the homework to do is 11:59 tonight. So right before midnight. Okay. And so the code snippet that I gave you, it looks like this, right? So first of all, we have to establish, you know, we have to create an empty matrix to hold in all of our values. So we have to do B. So we're going to use the zeros function for this, right? Right. And so this function right here is going to create an empty 5 by 5, right? And so that will basically give us a matrix of zeros. Okay? And then from here, we have a for loop, right? So you have for, and then there's a blank right here, okay? And then inside the for loop, we have an if else statement, right? So we have if, and then a box, and then box, okay? Else if, box, and then box, and then else. We have 2 boxes, right? And then we have an end. And then right under this, there's one more line of code, which I'll box it right there, okay? Okay. And so this is the problem. So in this problem, basically, you have to fill in all of these boxes, right? Okay. So we're filling in a matrix here. So I think, you know, following the logic from last week, you would think that, you know, we'd have a nested for loop from this, because, you know, a nested for loop is kind of the best way to visit every single entry. But in this case, you can see I've only given you one for loop, right? And so, you know, how do we actually go about doing this with one for loop? Right? And so you'll notice, you know, from the solution, that there's still, even though, you know, we have a matrix, a lot of the entries are still 0. Okay. And so the fact that a lot of them are 0 and we're starting with the zeros matrix means that, you know, we don't actually have to visit every single entry. We only have to visit the ones that are non-zero. Okay. And let me highlight the matrix like this to kind of give you some hints about how to go about this. Okay. All right. So I've circled the matrix like that to kind of highlight, you know, how, you know, our 3 different cases here, right? Because the fact that we have an if, else if, and else statement means that, you know, we're gonna have 3 different cases, right? And so let's look at the red case first. So in the red case, you know, we have a -2 on the diagonal and then a 1 on the right of the diagonal, right? And then we compare that to all the green rows. So for all the green rows, we again have a -2 on the diagonal, but we have a 1 on both sides of the diagonal, right? So we have 1 on the left and 1 on the right. And then for the blue row, you know, we have a -2 on the diagonal, and then we have a 1 on the left of that, okay? So that gives us some hints about what we can put into the if statements, right? Because these are going to be our 3 cases. So for the first if, let's say that if this is the first row, okay? Then for the else if, that'll we'll use the condition for the last row, okay? And then our else, you know, the else, remember, is going to be every other case. So this is going to be all other cases. Right. Oh, and one other thing. So the for loop, you know, we're going to loop from 1 to 5 because we have 5 rows, right? So you can think of this for loop visiting every single row in this matrix, okay? Okay. All right. And so now let's go ahead and fill in the other boxes where, you know, all of these boxes here, what we're going to do here is we're going to, you know, they're going to assign a value in the B matrix, okay? Right? So that's why all of these boxes here, they start with B. So actually, let's start at the very bottom. Okay, so let's start at the B that's outside of the if statement. Okay, and so the fact that this line at the very bottom here is outside the if statement means that this line of code is going to be executed on every single instant or every single iteration of the loop, right? And so if we look at our output here, what's something that happens on every single row of this matrix without fail, right? We set -2 to be on the diagonal, right? And so that's going to be our, every single case one, right? And so in this last one right here, we need to assign -2 to diagonal. Okay. And the way you can do that is you can actually use the loop index, right? And so let's say that our loop index here is I, right? And so one way that you can do the last line is you can say B at I, comma I is equal to -2. Okay. And so that'll go down there, right? Because that uses, because we know that I, which is our loop variable, is going to eventually count from 1 up until 5, right? And then, just by using that, then we can use that to assign entries in the matrix. Right? Okay. And so now that basically tells us that all the other B lines here, they're going to assign the off diagonal terms. Okay. Okay. And the way that we can assign off diagonal terms is we can again use the loop index. Okay. And so I'll give you a hint. So to assign the value to the right of the diagonal, we can do something like this, right? Right. And so this tells us, we want to reference the matrix B in row I, and then in the column I plus 1, right? And so that'll shift your column from the diagonal one over to the right. Okay. And so you can use lines of code like this inside, this for loop to basically, help you fill in that matrix altogether. Okay. Right. Does this help a little bit with that problem?
Yeah.
Great. Okay. Yeah. So that's kind of the logic behind that one. And this is going to be really important. So we're actually going to see this again on Wednesday. So I signed this very purposefully because we're going to use this exact loop in our implementation for finite differences. So definitely get familiar with this loop, because we're definitely going to be using it again, and we're going to be using it over and over and over again throughout this class. So if you understand the logic in this loop, you're going to be in great shape moving forward. Okay. Okay. All right. And so now let's go ahead and pick things up right where we left off last time, right? And so if you remember from last Wednesday, we had just gotten done talking about finite differences, right? And so the idea with finite differences is that you can basically use it to take a derivative and then turn it into an algebraic expression, right? Right. And so the formula, right. Yes. Yes. So so the question in the chat is, how do you use I plus 1? So that's where the if statement comes in. So you want to make sure that you use it in the right places so that you don't go out of bounds on the matrix. Right? Okay. And so the general formula for this looks something like this, right? So maybe we have d phi dx, right? And so we have a derivative of a function phi with respect to x. And so the way that we can approximate this might be something like this, right? We take the difference between the solution values at 2 locations in our grid, and we divide it by the grid spacing. Okay, and so that's kind of as a reference to maybe something that we have a line like this, right? And then we have our function values above this line, right? And so if we want to take the derivative, say at this location here, we'll call this location 3, right? What we can do is take the values of the function at locations 4 and 2, take their difference, and then divide it by the distance in between them. Okay, and there should be a 2 right there, right? And so the derivative at 3 be equal to 4 minus phi 2 all divided by 2 delta x. Okay, where delta x is the distance in between these two guys. Right? Right? And so this is going to be great for us because it'll allow us to basically transform a differential equation into an algebraic one, right? But we also spend a lot of time talking about that even though this is nice, it's not perfect, right? Because an algebraic expression will never be as perfect as a derivative in terms of calculating slopes and things like that, right? And so just by making this approximation, and that's the reason we call it an approximation, we're incurring some errors here. Okay. Okay. And by errors, what I mean is that what we compute from finite difference, there's going to be some differences between that and what it actually is, mathematically, right? And we spent a long time talking about those errors in terms of its Taylor series, right? And so this particular error, or the error that you get from approximating a derivative in terms of a finite difference, this was known as truncation error. Okay. And the reason it gets that name is because we're essentially truncating the Taylor series, right? And so if you remember, we only considered the first few terms, the Taylor series approximation, but we kind of just ignored everything else. Everyone else, we don't care about you, right? And so by truncating all those other terms, even though their contributions might be small, they're still significant, right? And so the fact that you're truncating things off means that you're going to incur some errors due to that. Okay. Okay. And so the other error that we talked about right before we left was this concept of round-off errors. Right? And so the idea with round-off errors is that, because we'll be doing these computations in the computer, oftentimes we'll get irrational numbers for the decimals, right? Right. And so, just in terms of computer memory, the computer can't keep computing decimal places for this. So at a certain point, it has to kind of round it off or cut it off, right? And so let's say that we cut it off here, right? And so we're only going to save that many digits in the computer. So since we're rounding all those other numbers off, there's going to be a little bit of error associated with that too. So usually round off error is pretty small, especially nowadays. Computers are pretty good. We have pretty good memories, but it's still there, right? And so it can be a little bit confusing to think about truncation error and round off because they seem kind of the same thing. Because in this case, you can think of it as we're truncating off the other decimal points, but they have very, very different definitions, right? Yes, this should be d theta. Yes, thank you. Okay. And so those are two main errors, right? So just a little bit of historical perspective. Round-off errors were a lot more significant when computers were more like potatoes, and so older computers wouldn't be able to store as many digits just because they were potatoes, right? But now that we have better, stronger computers, round-off errors becoming less and less of an issue just because we have we can have more memory. Bad potatoes. Okay, so there's one more error that I want to talk about, and it's a little bit more abstract in concept, and this is the idea of a modeling error. And so the idea of a modeling error doesn't just apply to this class. It actually applies to, every all your other classes too. And it's the fact that, it's the fact that reality is a very, very complex thing, right? It's very difficult. In a lot of cases, you can't find the perfect equation to perfectly model reality, right? Right. And so just as an example from your heat transfer classes, right? And so for your heat transfer classes, probably you've made some assumptions like, that this surface or a surface in your model might be perfectly insulated, right? But we know from reality that's impossible. You can't have a surface that's perfectly insulated, right? You can get pretty close, but it's never going to be exactly that, right? And so the fact that that it's hard to find perfect equations to to fit every situation, there's some modeling error with this, right? And there's also some user errors too, where even for those cases, you still have to pick the right equations to solve it, right? And so if you don't pick the right equation, so like let's say that you're solving a heat transfer problem, but for some reason you end up solving Navier-Stokes, right? In that case, you're solving the wrong equation for the wrong problem, and so that's what's called a modeling error, right? And so modeling error is more it's more to do with choosing the right equation, or the fact that the perfect equation out there just doesn't exist, right? There's a discrepancy between what happens in reality versus what we can actually model in the computer. Okay. And so that's the idea of modeling error. So anytime you have a mathematical equation, there's always that kind of modeling error, because there's no equation out there that can account for absolutely everything, right? And so you kind of just have to always remember that and kind of take any kind of mathematical result with the grain of salt. Okay. And so that's all I wanted to say about errors. And so now let's go ahead and move on to the next topic, which is actually solving equations, right? And so we've spent a long time talking about theory. So now let's actually put things into practice. Okay. And so where we're going to go from here is we're going to start with kind of the simplest equation that we can solve with these methods, which is the 1D diffusion equation. Okay. All right. And so just as a reminder, let me write out our general conservation equation. Okay. Right. And so our general conservation equation, we had our unsteady term. Then we had our convective terms. Okay. Then we had our diffusion terms. Right. Then we had our source term. Okay. So let me go ahead and label all these. So that's our unsteady term. Here's our convective terms. Okay. Here's our diffusion. And then this last guy right here, this is our source. Right? All right. So we'll eventually be able to solve this entire equation right here. But for now, that's a little bit too much to handle at once. And so the way that the next few weeks are going to go is that we're going to basically build up this equation kind of step by step. Okay. So for now, we're going to basically eliminate most of the terms in this equation and just focus on one or a couple or two at first. And then eventually, we'll keep adding terms up until we get this full thing. Okay. And so to start with, we're going to start with the 1D diffusion equation. And so that means we're going to take out this unsteady term. Okay. We're going to take out the convective terms, and then we're going to eliminate one of the diffusion terms. Okay. because we're not ready for the y derivative yet. So we're just going to stick with the x derivative. Right? And so after eliminating all those guys, what we're left with is this. Right? And so we have gamma. So remember, gamma is our diffusion coefficient. Okay. And then to that, we're going to add our source term. And then, because everything else canceled out, we're going to be equal to 0. Okay. And so this right here is our 1D diffusion equation. Right. You'll notice that I also changed the partial derivatives in that equation to regular derivatives, right? And the reason for that is, since now we only have one independent variable, since we just have x, we don't have y, we don't have t anymore, then all the derivatives just become regular derivatives, okay? And so what we're going to do here is we're going to, talk about how we can actually solve this with finite difference, okay? But in this particular case, we're actually very lucky because this right here, since it's just a first order, a second order ODE, we can actually also find the exact solutions. And so that's actually a big boon for us because what this will allow us to do is it'll allow us to verify and allow us to check our numerical results against something that we know for sure is correct, right? And so this is very rare. So very rare when you're doing computations, you have no idea, what the exact solution looks like. Well, you don't have no idea, but you don't have a very nice closed form mathematical solution, right? And so the reason we're starting with this is that solving the exact solution is we can do it, right? And so as we're developing the theory for finite differences, we can check against this exact solution just to make sure that we're on the right track and we're doing the right things. Okay. Okay. Any questions on this?
I guess if we're working on a problem for this, I guess what assumptions will be given in the problem such that you can mark unsteady and convective and part of that diffusion equation to 0.
Mm-hmm.
I guess, yeah, let's say we're working on a homework problem, is that going to be stated in the problem or?
Yeah. So for the way that the homeworks are going to work is that I'm just going to give you the equation straight up. I said, I'm going to please, just find the finite difference solution to this. So after, based on that, I've already eliminated all the terms that we don't need from the equation.
Okay.
Yeah. So for at least for this first part of the class, I want to really focus on just, how can we find the numerical solution. So, applying the assumptions and all that thing, I'll do that for you just so you can focus on just, the methods.
Got it. Thank you.
Mm-hmm. Okay. All right, so let's go ahead and start solving it. So let's actually start with the exact solutions, right? So we're going to do a little bit of refresher from 308 or wherever you learned your engineering math, right? Okay. All right. And so the first thing we'll note is that our equation here is a second order ODE. So ODE stands for ordinary differential equation, right? And the fact that it's second order, or in other words, since we have a second derivative, this means that in order to find a full solution, we're going to need two boundary conditions. Okay. And so let me draw out a 1D domain and let me specify by what I mean by boundary conditions. Okay. And so since we're in 1D, our domain is simply just going to be a line, right? And so, here we have our line, and let me give these two endpoints a name, right? And so the one on the left, we're going to call this the left-hand side. And on the right, this is going to be the right-hand side. And so our solution is going to take place in between those two extremes. Right? Okay. And so when I say we need to specify boundary conditions, what that means is that we need to specify how the solution is going to behave at the two boundaries of our domain. Okay. Okay. All right. And so in general, at least for this class, there are two types of boundary conditions that we can apply. Okay. Okay. And so I think I think you guys already kind of know what these are. I think the more difficult thing is going to be remembering the names for these. Because in computational math, they have very specific names for these types of boundary conditions. Okay, all right. So the first type of boundary condition that we'll talk about is called the Dirichlet boundary conditions. Right? And so that's spelled like this. Right. And so a Dirichlet boundary condition means that we're going to be directly specifying the solution value. Okay, and so mathematically it looks something like this, right? And so let's say that our solution function is phi of x, right? And so a Dirichlet boundary condition would look something like this, right? So let's say that we have phi of x is equal to x boundary, okay? And so that's either going to be the x coordinate of the left boundary or the x coordinate of the right boundary, okay? And so this Dirichlet boundary condition basically says that our solution has to take a value of this at our boundary, okay? And so here I have a Dirichlet boundary condition of phi naught, right? And so what this means is that when we're on the boundary xb, then the solution has to be x naught, okay? Or phi naught, sorry. Right? And so once we actually do an example, this should become a bit more clear. But for now, are there any questions on this? Okay. All right, so that's the first type of boundary condition. And so let's talk about the next kind, right? And so the second type of boundary condition is known as a Neumann boundary condition. And so a Neumann boundary condition, instead of applying the solution value, what we're going to be doing is applying the derivative of the solution. Okay, and so mathematically it looks something like this, right? And so we have d phi dx, okay? And if we evaluate this at x boundary, this is going to be some specified value. So in this case, I'm using a lowercase gamma for that. Right? And so basically, whenever we specify a derivative, then we're going to call that a Neumann boundary condition. Okay. Okay. So those are two types of boundary conditions. So next, we're going to do an example, and I'll help you kind of classify. We're going to solve through the entire example, and then I'll classify the boundary conditions for you. Okay. And so in this example, let's consider the following 1D equation. Okay. Let's say that our equation is something like this. We have d squared phi dx squared is equal to 6x. Okay. So pretty simple for starting out. Okay. And so let's say that our boundary conditions are given by the following. And so first, let's say our boundary condition at 0. And so let's say that we have a phi of 0, and we'll say that this is going to be equal to 1. Okay. And then our next boundary condition is going to be at x is equal to 1. Okay. And so let's say that the derivative at x is equal to 1 is equal to 0. Okay. All right. And so the first thing we can do, before we classify these boundary conditions, let's go ahead and show our domain. Okay. Okay. And so you can see here that we have one boundary condition at x is equal to 0, and so that's going to be the left-hand side of our domain. And then the other boundary condition is applied at x is equal to 1, and that's going to be the right-hand side. Okay. Okay. And so there's our domain. And so since our boundary conditions are at 0 and 1, then we're going to be solving the equation in between those guys. Okay. All right. And so now the boundary conditions, we know that they're going to be applied at the two ends of our domain, right? And so let's look at the first boundary condition, right? And so in the first boundary condition, what we're saying is that phi, which is our solution variable, has to take a value of 1 at x is equal to 0, okay? And so if we relate this to our, our definitions for the boundary conditions, we can say that this is a Dirichlet boundary condition, right? Because for Dirichlet boundary conditions, we're directly specifying the value of the function, okay? All right. And so our boundary condition on the other side is that d phi dx at x is equal to 1, this has to be 0, right? And so from our definition, since we know that we're applying the derivative of the function at this boundary, this has to be a Neumann boundary condition. Right? All right, so we have a Dirichlet condition on the left and a Neumann condition on the right. Okay. And so now that we've established that, we know what our boundary conditions are, we can go ahead and start integrating this guy to solve. Right? Because in this case, it's a pretty simple 1D equation, so we can just solve this by hand. All right, any questions on this so far? Okay. Okay, and so let's go ahead and integrate this guy. Right? And so we're lucky in this case, because we don't have any, it's not too complicated. So in order to solve for this, we can just simply integrate. Okay. All right, and so on the left-hand side, the integral will take care of one of the derivatives, and so all we're left with is d phi dx, okay? And then when we integrate 6x, what we get is 3x squared. Right? And since we're performing an indefinite integral, we need to add an arbitrary constant, okay? Okay. And then in order to get our full solution, we need to integrate again. And then what we get is phi of x is equal to x cubed plus c1x plus c2. All right. And so here is our general solution. And then from the general solution, we need to solve for the values of c1 and c2. And the way that we're going to do that is by applying our boundary conditions. Okay. Does this process seem familiar to everyone? Has everyone seen this before in like 308 before? Yes, no? All right. Okay, good. Good. Okay, so let's go ahead and start applying our boundary conditions. Okay, and so let's start with the Dirichlet boundary condition on the left, okay? Because, just kind of as a pro tip, whenever you have a boundary condition at 0, that's usually pretty nice to apply because it cancels out most things in the equation. Right? Right. Okay, and so at x is equal to 0, we're going ahead and plug that in, right? And so we have 0 cubed plus c1 times 0 plus c2, right? And then according to our boundary conditions, this has to equal to 1, okay? Question, is 526 similar to this class? I'm not actually sure what 526 is, so I need to go look that up. But then, you know, I'll have an answer for that next time. Okay. And so you can see here, you know, we've crossed out these guys, right? Since we're just multiplying them by 0. And then all we're left here is just C2 is equal to 1, right? And so that's pretty nice. Right? Next, we're going to have the Neumann condition on the right-hand side. Right? And so let's go ahead and take the derivative of our function. Right? So d phi dx is equal to 3x squared plus c1. Okay? And then let's evaluate this at x is equal to 1. Okay? All right. And so we have d phi dx at x is equal to 1. And this is going to be equal to 3 times 1 squared plus c1. Right? And according to our boundary condition, that has to equal 0. And so if we solve this equation for c1, what we get is c1 is equal to minus 3. Okay? All right. Any questions on this so far? Okay. All right. And so when we plug in C1 and C2, we get our exact solution, which is x cubed minus 3x plus 1. And so we can graph the solution and look something like this. Okay. And so our graph looks, it's going to start at phi is equal to 1, and then it's going to go down just like that. Okay. So this is 1, and down here is like minus 1. You see we have just like that. This is x is equal to 1. Obviously, this is x equal to 0. Okay. And so our graph is kind of almost looks like a decaying function, just like that. Okay. So that's all good. You know, so that's one way to solve this problem. But you know, this class isn't a repeat of 308, and so we're not going to be doing this just like that, because we want to solve this using MATLAB, right? Or we want to put this problem in a form that a computer can solve this, right? And so let's see how we can actually solve this using finite difference. Okay. Okay. And so in order to actually do this, you know, we know that we have to do a couple steps, right? And so first of all, we know that we need to discretize our domain. Okay. And so that's the first step. And then the second step is to discretize our equation. Okay. Okay. And so, you know, we're going to do these two steps to solve the same equation using finite differences. Okay. And remember, the point of discretizing the equation right here is to turn our differential equation into an algebraic one. Okay. And so the goal here is to get an algebraic expression, okay, or equation. Okay. But let's start with discretizing the domain. Okay, so let me go ahead and draw our domain again. Okay. And so remember, our domain here in 1D is very simple. So it's just going to be a line, right? And so, when we say we want to discretize this, we want to break this up into, a bunch of smaller, simpler shapes, okay? And so in 1D, that might seem silly because, we have a line and you can't really get much simpler than a line. But what is easier to deal with than a line is a shorter line, right? And so let's actually break this up into a bunch of smaller lines. Okay. And so let's say all the shorter lines will look like that, okay? And then what I'm going to do here is I'm going to label all of these points with a number, right? Okay. And so in this case, I only have 9 nodes, right? And then the spacing in between each node, we're going to assume that we have the same spacing all around. We'll call that spacing delta x, okay? And so now that we've discretized our domain, we can start to use this grid here to discretize our equation. Okay. Okay. Any questions on this so far? Right, question? Yep. Okay. And so now that we have a discretized domain, we're ready to start discretizing our equation. And the way that we're going to do that is we're going to replace every derivative in our equation with a finite difference approximation. Okay. All right, so let's go look at our original equation here. So our original equation was d squared phi dx squared, right? This is equal to 6x, right? And so I'm going to do basically the same equation as our example, okay? And so if we replace this derivative here, we only have one derivative, right? With a finite difference approximation. And so here we need the finite difference approximation for a second order derivative. We get the following, right? Okay. And so by replacing that derivative with a finite difference, now we've essentially eliminated the derivative here, and now what we have is an algebraic expression. Okay. Okay. And so now that we've discretized our equation, let's go ahead and mash this up to our grid. Okay. And so if we have our grid here, okay. What this equation will allow us to do is it will allow us to solve for phi at each node in our grid. Okay. Okay. And so what we want eventually is a solution that looks like this. Right? And so if you remember what our exact solution looked like, it looks something like this. Okay. where this up here is phi 1, we'll call this phi 2, call this phi 3, phi 4, phi 5, phi 6, and phi 7, okay? And so this is what we want right here, right? And so the result of our finite difference approximation is we want to solve for the solution at each of the nodes in our mesh, okay? And ideally, we would want to look like our exact solution, right? So this is what we want. But at this point, you know, we haven't solved for the unknown. We haven't solved for those phi values, right? And so what we can basically say at this point is, you know, these phi values are going to be our goal. Right? And so our goal is to solve for each of the discrete values of phi at each of the nodes in our mesh. Right? Right. And so this is actually quite different. If you compare this to, you know, how we solved our exact solution, this is actually quite different, because in our exact solution, what we solved for was a function, right? So we solved for phi as a function of x. And so we can't do that anymore because we don't have, you know, x as a continuous variable. What we have instead is we have these discrete grid points on which, you know, we're going to solve the equation, right? So instead of solving for a continuous function, what we're solving for are discrete values of phi, okay? And we're going to use this finite difference equation that we have above to basically generate the algebraic equations that we need to solve for these phi values. Okay. Okay. Any questions on this so far? Okay. All right. And so let's, you know, before we start, let's actually count how many equations that we're going to need, right? And so let's count how many unknowns that we have here, right? And so we have 1, 2, 3, 4, 5, 6, 7, right? And so we have 7 unknowns. And so what this tells us is that we're going to need 7 equations, 7 algebraic equations to solve for those 7 unknowns, right? And the way that we're going to do that is we're going to basically keep applying this finite difference approximation, you know, over and over again until we get those 7 equations. Okay. All right, question. So for this thing, we only really know the left and right side solutions. Yeah, so we'll get to that later. So actually, you know, to actually solve for, you know, the solutions at phi 1 and phi 7, which is at the extremities, you know, we're going to need to apply our boundary conditions there. But all of that will come in due time. Yep. Okay. Okay. And so, you know, we'll call this the quest for the 7 equations. And so just as a matter of completeness, let me go ahead and write down the equation that we had, the finite difference equation, right? And so our finite difference equation look like this, right? Okay. Okay. And so let's remember what the i's in this equation stand for. And so the i's in this equation, they stand for the different nodes in our grid, right? And so in this case, our i's go between 1 and 7, right? Okay. Because we have 7 nodes, right? But this finite difference equation here is general. And so this works for any of the i's, right? And so let's take this equation and let's evaluate it at I is equal to 1, or let's evaluate I is equal to 2, right? Sorry. Okay. And so if we set I is equal to 2, you know, we're going to get the following equation, right? And so first thing we have is phi of I minus 1. And so we have phi of 2 minus 1, which is phi of 1. Okay. Then we have 2 minus 2 times phi of I. And since I is 2, we're going to have minus 2 phi 2. Right. Then to that, we're going to add phi of I plus 1, which is going to be phi 3. Okay. And on the right-hand side, we have 6 times x2, where x2 is the x-coordinate for grid point number 2, okay? And we have over x squared. All right, and so just to kind of simplify this, let me multiply both sides by delta x squared. Okay, and that gives us, believe it or not, our first equation. And so, just like that, we already have our first algebraic equation, right? And so that's 1 out of 7. And so now we need to find the other 7 equations, but we can do this by just simply applying that same finite difference expression at the different nodes, right? And so now let's do the same thing, but let's set I is equal to 3, okay? And so if we set I is equal to 3, what we get is phi 2 minus 2 phi 3 plus phi 4 all divided by delta x squared. And this is equal to 6x3, okay? We again multiply both sides by x squared. Delta x squared, right? And then what we get is phi 2 minus 2 phi 3 plus phi 4 is equal to 6x3 delta x squared, right? And then here we have our second equation, right? And so as you can imagine, we can keep applying this over and over again until we get all of our equations, okay? And so I'm going to continue that on the next page, but are there any questions on this page before I move on to the next one? Okay. All right, and so let's continue on. And so let's set I is equal to 4. Okay. And so I is equal to 4. And so I'm just going to go ahead and skip to the result here. We'll give us phi 3 minus 4, or 2 phi 4, sorry. Jump the gun there. Plus phi 5 is equal to 6x4 delta x squared, right? And so this is equation number 3. Okay, next we're going to set I is equal to 5, and we get phi 4 minus 2 phi 5 plus phi 6 is equal to 6x5 delta x squared, right? So that's our fourth equation. And then we're going to set I is equal to 6. Okay. And that's equation number 5. Okay. And so just by applying the exact same finite difference formula, you can see that we've already generated 5 out of 7 of the equations. Okay. And so they look all very similar because they should all be pretty similar because they're all based on the same equation. But these are actually all unique equations because they involve different sets of unknowns. Okay. Okay. And so that's great. And but what you should have noticed from the beginning is that I started counting at I is equal to 2, right? And so why did I not use I is equal to 1 and I is equal to 7. Okay. Right. And the reason for that is that these nodes are on the boundary. Okay. Right. And so you can't apply your finite difference approximation onto your boundary nodes because it's just going to, give you something nonsensical, right? And so just as an example, let's start with I is equal to 1. Okay. And so if I is equal to 1, what we have is phi of 0 minus 2 phi 1 plus phi 2 is equal to 6x1 delta x squared. Okay. Okay. And so at first this might seem okay, but you look at phi 0, and then we say that this guy doesn't exist in our mesh. Right? Because remember, for our grid, we started counting at 1, right? So you can see, our leftmost node here is 1. And so if we wanted to get a phi 0, it would exist somewhere on the left side of this grid, right? But as far as we know, or as far as we care, there's nothing on the left side of this grid, right? And so since phi 0 doesn't exist here, we can't actually apply our finite difference approximation for that, okay? And so this whole equation can't be used because phi 0 doesn't exist. Okay, and you can do the exact same exercise for I is equal to 7. Okay, and so at I is equal to 7, you're going to get a phi 8 from our finite difference approximation, which doesn't exist because it's beyond the scope of our domain. Okay. Okay. And so now we're kind of stuck a little bit because we know that we need 2 more equations, right? So because right now we only have 5 of the 7, but we can't apply our finite difference approximation on our boundary nodes, okay? And so what do we do in these cases? And so in these cases, what we can do is we can apply our boundary conditions. Okay? Okay. Because remember, the boundary conditions are, they're going to define how our solution behaves at our boundaries. Okay. Okay. And so now the distinction of our Dirichlet and Neumann boundary conditions are really going to come into play because that's going to help us actually create these equations. Okay. All right. And so let's start with the Dirichlet boundary condition on the left-hand side. Okay, and so our Dirichlet boundary condition looked like this. From our original problem, we basically says that phi of 0 has to equal 1. Okay. Okay. And so, this says that at x is equal to 0, phi must equal to 1. Okay. All right. And so let's find the node where x is equal to 0. Okay. All right. And so we go back to our domain here, and we go and we see our, our segmented line from 1 to 7, right? And we see that the left-hand side of this domain is, or the node that's sitting on the left-hand side of this domain is 1, right? And so the node where x is equal to 0 is going to be node 1. Right? And so to apply this boundary condition, what we are basically saying is that the the solution must take a value of 1 at the leftmost at the leftmost part of the domain, right? And so mathematically, we can say this, right? And so we can say that phi1, which is the solution, our solution at node 1, has to equal 1. Okay. Right. And so believe it or not, this is an equation, right? And so this is equation 6. Okay. It's a very simple equation. It basically just says that, phi1 has to equal 1, but it's an equation, right? It's going to be something that helps us solve for, one of the unknown solution variables, right? And so just by that, it's one of our equations, okay? And so in general, what you'll find for these 1D problems is that each boundary condition will give you one additional equation that you're going to need to solve your system, okay? And so generally the way that, you're going to discretize these problems is you're going to apply the finite difference for all the interior nodes in your domain, right? So that's all the nodes that aren't on the boundary. And then for your two boundary nodes, you're going to apply some kind of boundary conditions in order to get those last two equations, okay? And so right here, we've applied the Dirichlet boundary condition to get our equation for the leftmost node. And then all we have to do now is apply the Neumann boundary condition on the right in order to get our 7th and final equation. Okay. All right, any questions on this? Right, so question in the chat. So could I go over again how it was equal to 1? Are we just assuming that the largest value to be 1? Yeah. No, so I'm giving it a value of 1 because that's kind of what it was defined with in the problem, right? And so your boundary conditions are going to be different for every single problem that you do. It's just that in this particular equation, we have the following boundary value problem. I guess I should have written it again here too, where that phi of 0 is equal to 1, and then d phi dx at x is equal to 1 is equal to 0, right? And so since in this problem we were given this boundary condition right here, this tells us that the solution must take a value of 1 at that boundary. Right, yes. Yeah, so for these problems, you're going to be given the boundary conditions for the problem. So it's all you guys have to worry about is discretizing it and putting it into an algebraic equation. Yeah. Mm-hmm. Yeah, good question. Right. Any other questions on any other questions on this? Okay, and so let's do the Neumann boundary condition. Okay. All right, so the Neumann boundary condition on the right-hand side was like this. Right? And so it basically says that the derivative of the solution at x is equal to 1 is equal to 0. Okay. And so once again, let's find out which node that we're going to apply this on. Right. Right. And so let's look at our domain and find out which node corresponds to the point x is equal to 1. Right. Okay. And so you remember from when we did the exact solution, the extremities of the domain are x is equal to 0 on the left-hand side, and then x is equal to 1 on the right-hand side. Right? And so since we're looking for the node where x is equal to 1, that's going to be our rightmost node in our grid. Okay. And so on this particular grid, we have 7 nodes. And so our rightmost node here will be node number 7. Okay. And so this Neumann boundary condition will basically be an equation that needs to involve phi 7. Okay. 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 And so we have here a derivative expression, right? And so we know that whenever we come across any derivatives in this class, what we're going to do is we're going to replace it with some kind of discretization. Okay. And so in particular, since we just got finished learning it, let's go replace this with a finite difference approximation. Okay. All right. And then let's apply this around I is equal to 7. Okay. And so first thing, let's do a finite difference approximation for a first order derivative, right? And so a first order derivative, remember we had 3 different options. So we could either do forward difference, backward difference, or central difference. Right? And so let's try with the central difference scheme first. Okay. And so with the central difference scheme, with I is equal to 7, we have the following. So we have I plus 1 minus phi of I minus 1, okay, all divided by 2 delta x, okay, is equal to 0. And so if we plug in I is equal to 7, what we get is phi 8 minus phi 6 divided by 2 delta x is equal to 0, right? Okay. But we have a problem here, right? And the problem is phi 8. Right? And since our grid only goes up to 7 nodes, phi 8 just doesn't exist, right? And if it doesn't exist, then we can't use this equation, right? And so we're kind of stuck here. And so what we can do instead is that instead of using a central difference scheme, let's use a different one that doesn't have phi I plus 1, right? So let's try backward difference. Okay. And so with backward difference, that's going to help us avoid going beyond our domain here. Okay. Okay. And so our formula for backward difference looks like the following. Okay. And so in this case, we're going to set the derivative equal to 0. And then let's again set I is equal to 7. Right? And so we have phi 7 minus phi 6 divided by delta x is equal to 0. Okay. Right. And then we check the phi values in there, and we can see that we're good to go because we have phi 7, which obviously exists because that's the one we want to solve for, right? And we also have phi 6, which also exists. Right? And so this guy finally is our 7th equation. Okay. All right. And so we're basically there, right? And so now, now that we have all 7 of our equations, we can summon the 7-headed Exodia. No, I'm kidding. Now we can finally put together our system of 7 equations for 7 unknowns, so that we can finally solve this system. Right? Okay, so let me write down all 7 of our equations right here, just so you can kind of see them all at once. Right? Right, so we have I is equal to 1, then we have I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5, I is equal to 6, and I is equal to 7. Okay. And so now let's go ahead and write down all of our equations here, right? Okay. And so at I is equal to 1, we had our Dirichlet boundary condition, right? And so our Dirichlet boundary condition says that phi1 is equal to 1. Okay. Next, we have all of our interior equations, right? And so we have phi1 minus 2 phi2 plus phi3 is equal to 6x2 delta x squared. Okay. Right. Then we have the equation for I is equal to 3. Okay. Then we have the equation for I is equal to 4, right? Then we have the equation for I is equal to 5. Okay. Then we have the equation for I is equal to 6. Right. And then finally, we have our Neumann boundary condition, which we just found up here. Let me cancel out delta x from both sides. And we have minus phi6 plus phi7 is equal to 0. Right. And so here are our 7 equations and 7 for our 7 unknowns. Okay. Right. So remember, we got 5 of these equations. 5 of these equations from our finite difference approximation. We got 1 of these equations from the Dirichlet boundary condition. And then we got our last equation here from our Neumann boundary condition. Okay. All right. So last thing I'm going to do here before I leave you guys is I'm going to take these equations here and put it in matrix form. Okay. So let me go ahead and do that. And so for our matrix form, we're going to need a 7 by 7 matrix. And so let me write out all the coefficients here. Right. So those are the first 6 rows. And then our last row looks something like this. Right. And so there's our solution vector. And on the right-hand side here, we have basically everything else. Okay. All right. And so, yes, and so you should see that we're right back where we are with problem 3C, right? So I told you that you'd see it again, but you probably didn't think you'd see it so soon, right? All right. Okay. And so, this is where I want to leave you for today. So on Wednesday, we're going to pick this up again, and I'll show you guys how to actually solve this in MATLAB, because here from this point, it's a little bit too, I know up to this point it's been cruel already, but it's unusually cruel to have you solve a 7 by 7 system by hand. So I'll show you how to take this system, put it in MATLAB, and have MATLAB do all the work for you, right? Okay, so thank you guys for tuning in today. Hope you guys enjoyed this lecture. Have a good evening, and I'll see you guys on Wednesday. Daniel, did you have any more questions? Okay, if not, I'm going to go ahead and close the call. So I'll see you on Wednesday.